Welcome to this explainer module. If you're joining us as part of our advanced computer science curriculum, get ready to dive deep today. We're going to rigorously deconstruct the limitations of relational databases, and then we're going to explore the theoretical foundations and the actual real-world applications of the W3C Open Semantic Standards. We aren't just talking about abstract theory here. This is literally about redesigning how machines understand information on a global scale. So let's just jump right into it.
Our syllabus for this explainer covers 5 key areas. We've got relational architecture failures, epistemology and data primitives, the W3C semantic stack, virtual knowledge graphs, and finally, semantic AI and graph RAG.
Section 1. Relational Architecture Failures.
To really understand why traditional data architectures fail to scale at the semantic level, we have to look at their structural flaws. Basically, traditional relational databases and even document stores force this arbitrary, rigid hierarchy onto your domain concepts. They tightly couple the actual meaning of the data directly to the physical storage implementation. And what's the result? Well, the exact moment that data crosses a system boundary, its context is completely lost.
This tight coupling creates massive enterprise friction. We're talking about schema rigidity, locking up data while systems evolve, and tightly coupled business logic just getting buried in incredibly fragile ETL pipelines. But honestly, the biggest offender here is identifier fragmentation. When you try to merge data across enterprise boundaries, foreign key collisions are basically inevitable. Think about it. An auto-incrementing primary key, say the number 5 in System A, bears absolutely no inherent mathematical relationship to a key in System B. So you end up needing these continuous, fragile translation layers just to keep the systems talking to each other.
Section 2. Epistemology and data primitives.
To escape all those legacy constraints, we have to fundamentally rethink data. We need to break data representation down to its epistemological axioms. So how do we solve that primary key collision problem? The answer is global identity. Semantic architectures adopt universal resource identifiers, or URIs. By replacing local, isolated primary keys with URIs, identity suddenly becomes globally addressable. Every single entity and class gets an unambiguous HTTP addressable namespace. And this is a game changer because it allows independently modeled datasets to just merge natively. No centralized key authorities, no messy key remapping pipelines.
Now, once we have global identity, we need a new way to actually structure the data itself. Enter the Resource Description Framework, commonly known as RDF. RDF atomizes all domain facts into binary relational primitives called triples. A triple is incredibly simple. It's just a subject, a predicate, and an object. Structurally, this means we can evaluate our data as a directed, labeled graph, right? The subjects and objects are the nodes, and the predicates are the edges connecting them. Because every triple is a completely self-contained fact, you get this amazing schema flexibility. You can fluidly attach attributes at runtime, and you don't have to alter underlying database structures or worry about DDL lockups.
Now, this brings us to a major paradigm shift for this curriculum. Let me pose a theoretical question to the class. What happens to a relational query when a fact is missing, compared to a semantic query operating under the open world assumption? Well, in traditional databases, which use a closed world assumption, if a record isn't found, the system conclusively assumes the statement is false. But semantic standards use the open world assumption. If a fact is unasserted, it's not false, it's simply unknown. This is absolutely vital because it accurately reflects real-world distributed enterprise data. Data in the real world is inherently incomplete.
Tied very closely to this is the unique name assumption. Traditional databases assume that 2 distinct keys automatically denote 2 distinct real-world entities. Open semantic standards explicitly reject this idea. By omitting the unique name assumption, automated inference engines can look at 2 distinct URIs and declare that they actually represent the exact same entity. They can then dynamically consolidate their properties, all without you having to build complex physical data merging pipelines.
Section 3. The W3C Semantic Stack.
Now that we've got the foundational epistemology covered, let's examine the mechanical layers of the W3C standards that actually operationalize this logic. Consider this your definitive syllabus for the stack. RDF handles the graph data representation, though its atomization does create some join overhead. Then you have OL2, which provides description logic reasoners for deductive inference. That means it can automatically deduce implicit knowledge, like knowing a manager is also an employee. But keep in mind, reasoning can induce query latency. Next is SHACL for structural validation, which requires maintaining shape definitions. And finally, SPARQL 1.1. This is your retrieval language, functioning much like SQL does for relational databases, though it can be computationally expensive when processing complex property paths.
I want to pause on shackle for a moment because it solves a really fascinating engineering paradox. Remember how OWL uses the open world assumption? Because of that, it literally cannot enforce constraint violations. If a field is missing, OWL just assumes the data exists somewhere else out there in the unasserted world. It won't flag an error. But obviously, in real-world enterprise engineering workflows, you need strict quality guarantees. So we use shackle, the shape's constraint language. Shackle essentially applies a closed-world assumption locally. It serves as a strict software quality gate at ingestion boundaries, ensuring invalid payloads are rejected before they ever enter your graph.
Section 4. Virtual Knowledge Graphs.
Let's look at how this operates at scale. Historically, a huge bottleneck was the idea that you had to physically copy petabytes of relational data into native triple stores, creating massive storage costs and latency. The solution to this is ontology-based data access, or OBDA, which you'll often hear called virtual knowledge graphs. OBDA exposes your legacy relational databases as virtual RDF graphs. You query the conceptual ontology using Sparkle, and the OBDA engine compiles that into native SQL using declarative R2RML mappings. This delegates the execution directly to those mature relational engines, without duplicating a single byte of raw data.
This brilliance operates through a four-part deterministic transformation algorithm. Step 1 is semantic expansion, where OWL axioms expands your Sparkle query to include things like subclasses. Step 2, mapping unfolding, uses R2RML mappings to replace those semantic terms with physical SQL subqueries. Step 3 is SQL optimization, where the engine eliminates redundant joins and pushes down filters. And finally, Step 4 is delegated execution, sending that highly optimized SQL directly to the legacy database. This proves exactly how we can query incredibly complex ontologies while still achieving real-time relational response times.
Section 5. Semantic AI and Graph RAG. For our final module, we're applying these architectures to arguably the most pressing challenge in modern computer science right now: generative AI data governance. Open semantic standards are the foundational infrastructure for modern data fabrics. A data fabric establishes a virtualized access layer across fragmented cloud environments and silos. By modeling your metadata as an RDF and OWL knowledge graph using standard vocabularies, you maintain decentralized query access and verifiable data lineage. But the best part? It completely removes vendor proprietary metadata lock-in. You are no longer hostage to a single vendor's architecture.
This semantic layer is also completely revolutionizing large language models through Graph RAG, or Retrieval Augmented Generation. Standard vector similarity search relies on text chunks and lacks structural precision, which, as we know, often leads to LLM hallucinations. Graph RAG fixes this. It grounds LLMs with deterministic context. It actually traverses the RDF graph via Sparkle to pull explicit multi-hop relational context. Furthermore, it validates the unstructured triples generated by LLMs against the OWL ontologies and shackle shape constraints. This filters out invalid facts before they can pollute the model's responses.
Now, a quick warning. Performing unrestricted reasoning dynamically at query time over millions of instances will cause your system to time out. To safely operationalize this in an enterprise architecture, you have to decouple inference from querying. You do this through a 5-step design. First, ingest raw facts explicitly. Second, define your logical rules separately in the terminology box. Third, materialize your inferences offline during batch jobs. Fourth, use lightweight virtualized query rewriting at runtime. And fifth, always enforce your shackle closed-world validation gates at ingestion boundaries.
As we wrap up this explainer and you reflect on today's curriculum, I want you to ponder this architectural paradigm shift. We've proven that we can fully decouple meaning from physical storage. So if meaning is no longer bound to the database table, what limits actually remain on how machines can autonomously infer and synthesize global knowledge? It's a huge question. Thank you for joining this deep dive into open semantic standards.